So here's something worth sitting with for a moment. Every rocket that has ever left this planet did so by doing something fundamentally violent. You take a tube, you fill it with something that burns ferociously, you light it, and you ride the explosion upward. That's it. That's the whole idea. And for all the elegance we've layered on top of it over the decades, the computer guidance, the carbon fiber, the mission patches and countdown clocks, underneath all of that, spaceflight is still a controlled catastrophe. You're balancing on a column of fire and hoping that every single one of the tens of thousands of components beneath you keeps doing its job for just a few more minutes. When it works, it's the most extraordinary thing human beings have ever accomplished. And when it doesn't work, the results are swift and terrible and seared into the memory of everyone who witnesses them. That's what we're going to talk about tonight. Not to be morbid, not to dwell on the worst moments for their own sake, but because the story of space exploration is inseparable from the story of its disasters. Every failure taught something. Every catastrophe rewrote the rules. The spacecraft you see launching today, the ones that carry astronauts to the International Space Station, the ones that land themselves on drone ships in the middle of the ocean, they are safer because of the people who died in earlier machines. That's a heavy thing to say, but it's true, and it's worth understanding how and why. So let's start at the very beginning. And by the beginning, I mean before anyone had even left the ground. The year is 1960. The place is a launch pad in Kazakhstan, at a facility the Soviets called the Baikonur Cosmodrome. Though it wasn't actually near the town of Baikonur, that was a deliberate misdirection, a fake name on the map to confuse Western intelligence. The real location was near a town called Turatam, out in the vast emptiness of the Kazakh steppe. And on October 24th of that year, the Soviets were preparing to launch a brand new intercontinental ballistic missile called the R-16. This wasn't a space mission exactly. It was a weapons test. But the story matters because it's one of the first times the particular pressures of the space race killed people on the ground, and it set a pattern that would echo for decades. The R-16 was the brainchild of Mikhail Yangel, a rocket designer who was competing with the more famous Sergei Korolev for resources and prestige within the Soviet missile program. And the man overseeing the launch that day was Marshal Mitrofan Nedalin, the head of the Soviet Strategic Rocket Forces. Nedalin was not an engineer. He was a military man, a political figure, and he was under enormous pressure to get this missile operational. The Americans were pulling ahead. Khrushchev wanted results. And so when problems started cropping up during the pre-launch preparations, and there were many problems, Nedalin pushed to keep going. Here's where it gets important to understand what was actually happening with the rocket. The R-16 used hypergolic propellants. That's a term you'll hear a lot in this story, so let's take a second with it. Hypergolic means the fuel and the oxidizer ignite on contact with each other. You don't need a spark. You don't need an ignition system. The moment these two liquids touch, they burn. That's useful because it makes engines simpler and more reliable. Fewer things to go wrong at ignition. But it also means that if those liquids ever meet when they're not supposed to, if a valve leaks, if a seal cracks, you have an instantaneous fire. And the specific chemicals used in the R-16, unsymmetrical dimethylhydrazine as the fuel and nitric acid as the oxidizer, were not just flammable. They were toxic, hideously toxic. The fumes alone could kill you. So the rocket is sitting on the pad, fully fueled with these nightmarish chemicals, and the technicians discover a problem with the control system. Specifically, there's an issue with the sequencing that's supposed to govern engine ignition. Now, the safe thing to do, The thing the engineers wanted to do was to drain the propellants, roll the rocket back, and fix the problem in a controlled environment. But draining hypergolic propellants from a fully loaded missile is a slow, dangerous process. It would take days, and Nedelin didn't have days. He had a deadline, and he had Khrushchev breathing down his neck. So Nedelin ordered the technicians to fix the problem on the pad with the rocket still fully fueled. And to show that he wasn't afraid, to demonstrate his confidence, he had a chair brought out and sat down about 20 meters from the base of the rocket. Dozens of engineers and military personnel were clustered around the pad, working on the fix. What happened next was the result of a cascading series of errors. During the repair work, a signal was inadvertently sent that activated the second stage engines. Not the first stage, the second stage, which sits on top of the first stage. The exhaust from those engines blasted directly downward into the fully fueled first stage below. The entire rocket became a fireball in an instant. The hypergolic propellants didn't just burn, they erupted. A massive wave of flames swept across the launch pad. Marshal Nedelin was killed immediately. So were most of the people near the rocket. Some who tried to run were caught by the burning propellant, which stuck to everything it touched. Others were poisoned by the toxic fumes, even if they escaped the flames. The exact death toll has been debated for decades because the Soviet government covered up the disaster completely. It didn't appear in any newspaper. The families of the dead were told their loved ones had died in a plane crash. Modern estimates put the number somewhere between 78 and 126 people killed. It remains one of the deadliest launch pad disasters in history, and for 30 years, the outside world didn't even know it had happened. The Nedelin catastrophe, that's what it's sometimes called now. It teaches you something fundamental about how space disasters happen. It wasn't one thing that went wrong. It was a chain. Political pressure led to schedule pressure. Schedule pressure led to cutting safety procedures. Cutting safety procedures put people in a place they should never have been, doing work that should never have been done with a live rocket. And then a technical failure, the errant signal, found all of those people exactly where they were most vulnerable. You'll see this pattern again and again. The technical failure is almost never the whole story. The technical failure is the last domino. The first dominoes are always human, organizational, political, cultural. Now, the Soviets learned from this, at least partially. They redesigned their safety protocols for fueling operations. But the culture of secrecy, the pressure to meet deadlines, the willingness to accept risks that no sane engineering process would tolerate, that didn't go away. It couldn't go away, because it was built into the structure of the Soviet space program, and we'll come back to that. But let's cross the ocean for a moment, because the Americans were having their own problems. In the late 1950s and early 1960s, the United States was trying desperately to catch up in the space race, and their early rockets had an almost comical tendency to explode. The Vanguard rocket, which was supposed to be America's answer to Sputnik, famously rose about 4 feet off the launch pad on December 6, 1957, lost thrust, settled back down, and detonated in a spectacular fireball on live television. The press called it Flopnik and Kaputnik. The satellite it was carrying, a tiny thing about the size of a grapefruit, was thrown clear of the explosion and landed in some bushes nearby, its radio transmitter still beeping away pathetically. It was humiliating. But nobody died, and that's an important distinction. The American program, for all its early failures, had a different relationship with risk, partly because it was operating in the open. When your rockets blow up on national television, You can't pretend it didn't happen. You have to fix it, publicly, and you have to explain what went wrong. But the Americans' luck with keeping people safe wouldn't hold forever, and the disaster that changed everything, the one that forced NASA to fundamentally rethink how it built spacecraft, happened not in orbit, not during a launch, but on the ground, in a place that should have been safe. January 27th, 1967, Cape Kennedy, Florida. Launch Complex 34. The Apollo 1 spacecraft is sitting on top of its Saturn 1B rocket, and inside the capsule are 3 astronauts, Gus Grissom, Ed White, and Roger Chaffee. They're running what's called a plugs-out test, basically a full dress rehearsal of the launch countdown, but with the rocket unfueled. No propellant in the tanks. The idea is to check all the spacecraft systems, make sure everything works, practice the procedures. It's supposed to be low risk. Nobody is even thinking about danger. The rocket has no fuel. What could go wrong? Here's what you need to understand about the Apollo 1 capsule. The atmosphere inside was pure oxygen at slightly above sea level pressure, about 16.7 pounds per square inch. Now, you breathe oxygen every day, obviously. The air around you is about 21% oxygen. But pure oxygen at that pressure is a completely different beast. In a pure oxygen environment, materials that would never burn in normal air become wildly flammable. Velcro, which was used extensively inside the capsule, burns like flash paper in pure oxygen. Nylon netting, aluminum, even certain metals, things you'd never think of as fire hazards, become fuel. And the Apollo 1 capsule was full of these materials. There was Velcro everywhere, used to secure equipment and checklists to the walls. There were bundles of wiring running behind panels. There was nylon netting beneath the seats. NASA knew that pure oxygen was a fire risk. They'd discussed it, but they'd been using pure oxygen atmospheres in spacecraft since the Mercury program, and they'd never had a fire. The reasoning was that pure oxygen was simpler and lighter than a mixed gas system. You didn't need the extra tanks and regulators for nitrogen. In the vacuum of space, the cabin pressure would be much lower, around 5 pounds per square inch, and at that lower pressure, the fire risk was significantly reduced. The problem was that during a ground test, the cabin had to be pressurized to at least 1 atmosphere to keep it from collapsing under the outside air pressure. So during ground tests, you had the worst possible combination, pure oxygen at high pressure. Grissom had been complaining about the spacecraft for months. He was a veteran. He'd flown in Mercury and Gemini, and he could tell that Apollo was having serious quality problems. There were wiring issues, equipment failures, things that didn't work right. At one point, he'd hung a lemon on the spacecraft simulator, the way you'd mark a bad used car. The relationship between the astronauts and North American Aviation, the company building the command module, was tense. But the schedule was the schedule. The goal was to land on the moon before the end of the decade. Kennedy's promise was hanging over everything, and there was no time to stop and fix things properly. So there they were, the 3 of them, sealed inside the capsule for the plugs-out test. The hatch was a complicated, heavy design that opened inward and required ratcheting bolts to secure. It took at least 90 seconds to open under the best conditions. The test had been plagued with communication problems all afternoon. At one point, Grissom, frustrated, said something like, "How are we going to get to the moon if we can't talk between 2 buildings?" And then, at 6:31 in the evening, one of the astronauts, likely Chaffee, said something over the radio. The exact words vary depending on the source, but it was something close to fire. "I smell fire." 2 seconds later, Ed White's voice, more urgent. "Fire in the cockpit." And then, almost immediately, a scream. The fire moved with terrifying speed. In a pure oxygen environment at that pressure, the flames propagated so fast that the astronauts had almost no time to react. Ed White, who was closest to the hatch, tried to open it, but the mounting pressure inside the capsule from the expanding hot gases actually pressed the inward opening hatch tighter into its frame. The internal pressure ruptured the cabin wall within about 15 seconds, and the rush of flame and toxic smoke that poured out drove back the pad workers who were trying to reach the hatch from outside. It took them 5 minutes to get the hatch open. By then, all 3 astronauts were dead, killed by the toxic atmosphere and the heat. Their suits had melted into the cabin interior. The investigation that followed was devastating. The review board found that the ignition source was almost certainly an electrical arc from damaged wiring. There were miles of wiring inside the capsule, and some of it had been abraded by repeated opening and closing of access panels during construction. But the fire's rapid spread was enabled by the pure oxygen atmosphere and the extraordinary amount of flammable material inside the cabin, and the crew's inability to escape was sealed by that inward opening hatch, which became physically impossible to open once the pressure inside began to rise. What happened after Apollo 1 is as important as the fire itself. NASA essentially stopped. They shut down the Apollo program for 20 months. They redesigned the hatch. The new one opened outward and could be operated in about 7 seconds. They replaced hundreds of pounds of flammable materials inside the capsule with fire-resistant alternatives. They changed the ground test atmosphere to a nitrogen-oxygen mix instead of pure oxygen. They rewired the entire command module. They created new flammability standards that still govern spacecraft design today. And they established a much more rigorous process for tracking and resolving engineering problems before they could accumulate into catastrophe. Some people have argued that the Apollo 1 fire, as terrible as it was, actually saved the program. That without it, the command module would have flown with all of those latent problems, and the disaster would have happened in space, where there would have been no chance of rescue and no chance of learning what went wrong. That's a painful kind of logic, but there's truth in it. The spacecraft that eventually carried astronauts to the moon was profoundly different from the one that killed Grissom, White, and Chaffee. It was better because of what they lost. And while NASA was rebuilding, on the other side of the world, the Soviet program was racing ahead with its own moon rocket, a massive troubled vehicle called the N-1, and a spacecraft called Soyuz that was about to have its own reckoning with the laws of physics. Vladimir Komarov knew his spacecraft wasn't ready. That's the part of this story that stays with you. He knew. His friend Yuri Gagarin knew. Engineers who had worked on the Soyuz 1 capsule knew. There were reports. Some accounts say as many as 200 structural problems had been identified before the flight. 200. And yet, on April 23, 1967, just 3 months after the Apollo 1 fire, Komarov climbed into Soyuz 1 and launched into orbit anyway. Why? Because the flight was scheduled to coincide with a politically important anniversary. The Soviet leadership wanted a spectacular mission, a rendezvous and docking between 2 crewed Soyuz spacecraft in orbit, with cosmonauts transferring between them. It would have been a stunning demonstration of Soviet capability, perfectly timed for propaganda purposes. Sound familiar? That same pattern we talked about with the Nedelin disaster. Political pressure overriding engineering judgment, schedules treated as more sacred than safety margins. Komarov was a test pilot, a military man, and by all accounts an extraordinarily brave and decent person. He and Gagarin were close friends. The story goes that Gagarin actually tried to bump Komarov from the flight, not because he wanted the glory, but because he thought the Soviets wouldn't dare risk their national hero on a spacecraft this troubled. If Gagarin showed up at the launch pad and insisted on flying, maybe they'd scrub the mission rather than risk killing the first man in space. But the plan didn't work. Komarov flew, and almost immediately, things went wrong. One of the 2 solar panels failed to deploy after reaching orbit. This meant the spacecraft had only half its electrical power. Systems started failing. The orientation sensors weren't working properly, making it difficult to control the spacecraft's attitude. The second Soyuz mission, which was supposed to launch the next day for the rendezvous, was canceled. Ground controllers worked through the night trying to help Komarov stabilize his crippled ship, and eventually the decision was made to bring him home early, on just the 18th orbit. Komarov managed to orient the spacecraft for re-entry manually, which was itself an impressive feat of piloting, given how degraded his systems were. He survived the blazing heat of atmospheric re-entry. The capsule slowed through the upper atmosphere, and then, at the moment when the main parachute was supposed to deploy and bring him gently to the ground, it didn't open. The drogue chute came out, but the main canopy stayed packed in its container. There was a backup parachute, but it tangled with the drogue. Soyuz 1 hit the ground at something like 40 meters per second, roughly 90 miles an hour, and then the retro rockets, which were designed to fire just before touchdown to cushion the landing, ignited in the wreckage and started a fire. Vladimir Komarov became the first person to die during a spaceflight. He was 40 years old. The investigation found that the parachute container had been improperly treated during manufacturing. The lining of the container was too rough or had been coated with a substance that created too much friction, and the main chute simply couldn't extract itself. It was stuck. Here's what's really sobering about that. This wasn't some exotic failure mode that nobody could have predicted. Parachute deployment is one of the most critical systems on any capsule, and the manufacturing quality control that would have caught this problem simply wasn't rigorous enough. The 200 problems that engineers had flagged before the flight, some of them were exactly this kind of thing. Workmanship issues, quality control gaps, systems that hadn't been tested thoroughly enough. And think about the chain of decisions that led to this moment. Each one individually might have seemed manageable. The schedule pressure? Well, schedules are always tight. The unresolved engineering problems? Well, there are always open items before a flight. You have to make judgment calls about which ones are acceptable risks. The political importance of the mission? That's just the reality of a government-funded program. But stacked together, those decisions created a situation where a man was launched in a spacecraft that wasn't ready and died because of a manufacturing defect that better quality control would have caught. Now, here's something worth sitting with for a moment. The Apollo 1 fire and the Soyuz 1 crash happened within 3 months of each other, on opposite sides of the Cold War. Both were caused, at the deepest level, by the same thing: schedule pressure and organizational failures that allowed known problems to persist until they became fatal. The Americans lost 3 astronauts on the ground and responded by stopping everything, redesigning their spacecraft, and fundamentally changing how they managed risk. The Soviets lost a cosmonaut in flight and, well, they made improvements to Soyuz, certainly. The parachute system was redesigned, but the broader organizational culture, the deference to political schedules, the pressure to fly before systems were proven, that took much longer to change. And the secrecy surrounding the program meant that the full lessons of Komarov's death weren't widely shared, even within the Soviet space community, the way the Apollo 1 lessons were disseminated throughout NASA. Soyuz did eventually become one of the most reliable spacecraft ever built. The basic design is still flying today, more than 50 years later, carrying crews to the International Space Station. But it took years of testing, redesign, and, painfully, more failures before it earned that reputation. Meanwhile, the Soviets were also working on their moon rocket, the N-1. And this is one of the great what-if stories of the space age, because the N-1 was an audaciously ambitious machine that never once flew successfully. Picture this. The Saturn V that NASA used to reach the moon had 5 enormous F-1 engines in its first stage. 5 engines, each one about 12 feet across, generating 1.5 million pounds of thrust. The engineering of those engines was incredibly difficult. They had problems with combustion instability that took years to solve. But the basic concept was manageable. 5 big engines. You can test each one individually. You can understand how they interact. The Soviet Union didn't have an engine like the F-1. Their rocket engine technology was excellent in many ways, actually superior to American technology in some respects. But they hadn't developed a single engine powerful enough to do what the F-1 did. So, the chief designer of the N-1, which by this point was being led by Vasily Mishin after Sergei Korolev's death in 1966, made a fateful decision. Instead of 5 massive engines, the first stage of the N-1 would use 30 smaller engines arranged in 2 concentric rings around the base of the rocket. 30 engines. Think about that. 30 separate combustion chambers, 30 sets of turbopumps, 30 fuel lines, 30 sets of things that could go wrong. And all of them had to work together, in concert, with their vibrations and exhaust plumes interacting in ways that were extraordinarily difficult to predict. Here's the thing about rocket engines. They don't just sit there and burn quietly. They shake. They vibrate. They create complex pressure waves in the combustion chamber. When you have 30 of them clustered together at the base of a rocket, those vibrations can interact with each other and with the structure of the rocket itself in ways that create resonance, the same phenomenon that can cause a bridge to shake itself apart if soldiers march across it in step. The technical term is pogo oscillation when it happens longitudinally, and there are other modes of vibration that can occur laterally and in torsion. Managing all of this with 30 engines was a problem that pushed the boundaries of what Soviet engineers could analyze and control with the computational tools available to them in the late 1960s. And here's what made it worse. They never did a full static test firing of the first stage before flight. The Americans tested each Saturn V stage extensively on the ground before it ever flew. They built massive test stands. They bolted the stages down and fired them at full power and measured everything. The Soviets, partly due to budget constraints and partly due to schedule pressure, there's that phrase again, decided that the N-1's first stage was too large to test on the ground. They would test it by flying it. The philosophy was essentially, let's launch it and see what happens. What happened was not good. The first N-1 launch attempt was on February 21st, 1969, just 5 months before Apollo 11 would land on the moon. The rocket lifted off, and almost immediately, there were problems. A fire broke out in the engine compartment. The engine control system, called CORD, shut down engines it thought were malfunctioning, but it also mistakenly shut down healthy engines. About 70 seconds into flight, the rocket was commanded to shut down all engines and was destroyed by the range safety system. It crashed downrange. The second attempt was worse. July 3rd, 1969, just 2 weeks before Apollo 11. The N-1 lifted off, rose to maybe 100 meters, and then one of the engines exploded. The cord system shut down all 30 first-stage engines. The rocket, now producing no thrust, settled back onto the launch pad. Fully fueled, nearly 2,300 tons of kerosene and liquid oxygen. The explosion was one of the largest non-nuclear blasts in history. It destroyed the launch pad completely. It shattered windows in buildings miles away. The fireball was visible from enormous distances. Remarkably, no one was killed. The area had been evacuated. But the launch complex was devastated. It took nearly 2 years to rebuild. There were 2 more N-1 launch attempts after that, in 1971 and 1972. Both failed during first-stage flight due to structural and engine problems. The rocket never made it past the first-stage burn, not once in 4 attempts. The program was eventually canceled in 1974, and the remaining hardware was scrapped. Some of the engines, the NK-33s, designed by the brilliant engine designer Nikolai Kuznetsov, were so well made that they were put into storage, and decades later, after the Cold War ended, American companies actually purchased them and used them on their own rockets. The engines themselves were excellent. The problem was never the individual components. It was the system. 30 engines, interacting in ways that couldn't be adequately predicted or controlled, on a rocket that had never been tested as an integrated whole before it was asked to fly. And this brings us to something fundamental about engineering disasters, something that comes up again and again. The failure isn't usually in the part. It's in the interface. It's in the space between components, between teams, between what one group assumes and what another group builds. The N-1's engines worked beautifully on the test stand, one at a time. It was only when you put 30 of them together, with their vibrations coupling and their exhaust plumes interacting and their control system trying to manage all of them simultaneously, that the problems became unmanageable. The Soviets learned this the hard way, and the cost wasn't measured in lives. Nobody died in the N-1 explosions, but in years and resources and, ultimately, in the moon race itself. By the time the N-1 program was canceled, Apollo had already landed on the moon 6 times. The race was over. But the story of Soyuz wasn't finished. Remember, I mentioned that the basic Soyuz design eventually became one of the most reliable spacecraft ever flown. That evolution involved more tragedy. On June 30th, 1971, the crew of Soyuz 11 undocked from the world's first space station, Salyut 1, after spending 23 days in orbit, a new record for spaceflight duration. Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev had just completed the most successful Soviet space mission in years. They were coming home as heroes. The re-entry and parachute deployment went perfectly. The lessons of Komarov's death had been learned, and the landing system worked exactly as designed. But when the recovery teams opened the hatch, they found all 3 cosmonauts dead in their seats. What had happened was something quiet and invisible. During the separation of the orbital module from the descent module, a routine event that happens high above the atmosphere, a pressure equalization valve had opened prematurely. This valve was designed to crack open at lower altitudes to equalize the cabin pressure with the outside atmosphere before landing. But a pyrotechnic bolt during module separation jolted it open while the spacecraft was still in the vacuum of space. The cabin depressurized in seconds. The cosmonauts weren't wearing pressure suits. The Soyuz capsule was so small that 3 crew members in spacesuits simply didn't fit, so the decision had been made to fly without them. They had no protection against the vacuum. And in a vacuum, consciousness lasts maybe 15 seconds. Death follows in under a minute. There was nothing they could have done, even if they'd realized what was happening. The air was simply gone. Now think about that for a second. Everything else worked. The spacecraft performed beautifully. The parachutes deployed on time. The landing was soft. And 3 men were dead because of a single valve, about the size of a coin, that opened a few minutes too early. It's one of the most quietly devastating disasters in the history of spaceflight, because there was no explosion, no fireball, no dramatic malfunction. Just a tiny mechanical event in the wrong sequence, and silence. The Soviet response was, in this case, genuinely thorough. They redesigned the Soyuz capsule. The most immediate change was the most obvious one. From that point forward, all cosmonauts would wear pressure suits during launch, re-entry, and any orbital maneuver involving module separation. Full stop. No exceptions. But here's the thing. Making that change meant something else had to give. 3 cosmonauts in pressure suits still didn't fit inside the Soyuz descent module. The capsule was just too cramped. So for the next several years, Soyuz missions flew with only 2 crew members instead of 3. They literally gave up a third of their crew capacity to ensure the remaining 2 could survive a depressurization. It wasn't until the Soyuz T variant arrived in the early 1980s that the capsule was redesigned enough to accommodate 3 suited cosmonauts again. And that valve, the one that killed them, was redesigned too. They changed the mechanism so it couldn't be jolted open by the pyrotechnic separation bolts. They added manual controls so the crew could close it themselves if something went wrong. They essentially built in redundancy for a failure mode that nobody had seriously considered before June 30th, 1971. Here's what's worth sitting with for a moment. The Soyuz spacecraft, after all of this, after Komarov, after Soyuz 11, went on to become arguably the most reliable crewed spacecraft in history. It's still flying today, or at least variants of it are. The basic architecture that was refined through those terrible losses carried cosmonauts and astronauts to space stations for over 50 years. Thousands of people have ridden Soyuz vehicles to orbit and back, and the reason it became so reliable is precisely because those failures happened and were taken seriously. Every death taught something specific, and the design was changed to reflect that lesson. The Soyuz is reliable not because it was brilliantly designed from the start. It wasn't really. But because it was iteratively corrected through decades of use, including corrections written in blood. And this is a pattern you'll see again and again in spaceflight. The systems that become the safest are often the ones that failed catastrophically early in their lives, because those failures forced the kind of deep, honest engineering review that prevents the next disaster. The dangerous systems are sometimes the ones that have never failed, because everyone assumes they're fine, and the hidden weaknesses never get exposed until the worst possible moment. Which brings us, inevitably, to the Space Shuttle. The Space Shuttle is probably the most complicated machine ever routinely operated. I want you to hold that thought, because it matters for understanding everything that went wrong. This wasn't a capsule on top of a rocket. This was a winged orbiter the size of a medium airliner, strapped to an enormous external fuel tank and 2 solid rocket boosters, launching vertically like a rocket and landing horizontally like a glider. It had over 2.5 million parts. Its main engines operated at temperatures and pressures that pushed the absolute limits of materials science. Its thermal protection system, the tiles and blankets that kept it from burning up on re-entry, consisted of more than 20,000 individual pieces, each one unique, each one bonded to the aluminum skin of the orbiter. The shuttle was born out of a political compromise, and this matters. After Apollo, NASA wanted to keep flying. The original vision in the early 1970s was a fully reusable two-stage system, a crewed booster that would fly back and land, carrying a smaller orbiter to space. That would have been elegant. It also would have been enormously expensive to develop. The Nixon administration said no to the full price tag, but yes to a scaled-down version. What emerged was a partially reusable system. The orbiter and the solid rocket boosters were reusable, but the massive external tank was expendable, discarded after every flight. This compromise meant the shuttle was never as cheap to operate as promised. Each flight was supposed to cost something like $10 to $20 million. The actual cost ended up being somewhere around $500 million to over $1 billion per mission, depending on how you count. But more importantly, the design compromises introduced engineering challenges that would have profound consequences. Let's talk about the solid rocket boosters, because that's where the first shuttle disaster begins. Each booster was about 149 feet tall and 12 feet in diameter, and they provided most of the thrust during the first 2 minutes of flight, roughly 70% of the total liftoff thrust. They burned a mixture of aluminum powder, ammonium perchlorate, and a polymer binder. Once you ignited a solid rocket, you couldn't shut it off. There was no throttle, no abort. It burned until the fuel was gone. That alone should give you pause. Now, these boosters were manufactured in Utah by Morton Thiokol. And here's a critical detail. They were made in segments. Each booster was assembled from cylindrical sections that were cast separately and then stacked together at Kennedy Space Center. The joints between these segments were called field joints because they were assembled in the field rather than at the factory. Each field joint was sealed by 2 rubber O-rings, essentially giant rubber gaskets about 1/4 inch thick and 37 feet in circumference, that sat in grooves and were supposed to compress and seal when the joint flexed under the enormous pressure of ignition. This is where everything hinges. The O-rings were made of a fluoroelastomer, a synthetic rubber compound, and like all rubber, their ability to flex and spring back into shape was affected by temperature. When rubber gets cold, it gets stiff. It loses its resilience, its ability to bounce back quickly. You can try this yourself. Put a rubber band in the freezer for a while, then take it out and stretch it. It doesn't snap back the way it does at room temperature. It's sluggish, slow, brittle even. Engineers at Morton Thiokol knew this. They had data going back years showing that the O-rings performed worse in cold weather. After several flights, they'd recovered the boosters from the ocean and inspected the joints, and they found evidence of what they called blow-by. Hot combustion gases getting past the primary O-ring and sometimes reaching the secondary one. This wasn't supposed to happen at all. The primary O-ring was supposed to seal completely. The secondary was a backup, a redundancy. But on some flights, especially cooler ones, the hot gases were getting past the first seal. The rubber wasn't springing into the gap fast enough. By 1985, some engineers at Thiokol were genuinely alarmed. Roger Boisjoli, a mechanical engineer who specialized in seals and joints, had been writing memos for months, warning that the O-ring erosion problem was serious and could lead to a catastrophic failure. He wasn't a crank or a whistleblower looking for attention. He was a quiet, methodical engineer who looked at the data and saw a trend that terrified him. In one memo from July 1985, he wrote that if the problem wasn't fixed, the result could be a catastrophe of the highest order, meaning loss of human life. He used those exact words, But here's where the organizational story becomes as important as the engineering story. NASA was under enormous pressure to fly the shuttle on a frequent schedule. The shuttle had been sold to Congress partly as a space truck, a routine, almost airline-like operation that would make space access cheap and frequent. By the mid-1980s, NASA was trying to launch something like 24 missions a year. The reality was that preparing each shuttle for flight was an incredibly labor-intensive process that took months. The schedule pressure was relentless, and within that pressure, the O-ring erosion had been gradually normalized. Each time a flight came back with evidence of blow-by and nothing catastrophic had happened, it became a little easier to accept. Engineers would note the erosion, managers would review it, and the conclusion would be that it was an acceptable risk because the secondary O-ring provided backup. The problem was reclassified from a potential flight safety issue to an acceptable anomaly. This is what sociologist Diane Vaughan later called the normalization of deviance. It's one of the most important concepts in engineering safety, and it applies far beyond spaceflight. The idea is simple and terrifying. When a system repeatedly deviates from its design specifications without immediate consequences, people gradually come to accept the deviation as normal. The boundary of what's considered safe quietly shifts. Nobody makes a single dramatic decision to accept danger. Instead, 100 small decisions, each seemingly reasonable in context, accumulate until the organization is operating well outside its original safety margins without anyone quite realizing it. On the evening of January 27, 1986, the temperature at Kennedy Space Center was dropping. The forecast for the next morning, the morning of the Challenger launch, called for temperatures in the low 20s Fahrenheit, well below freezing. This would be the coldest launch in shuttle history by a significant margin. The previous coldest launch had been at 53 degrees, and that flight had shown the worst O-ring erosion yet observed. Roger Boisjoli and his colleagues at Thiokol were deeply worried. A teleconference was organized between Thiokol engineers in Utah and NASA managers at Marshall Space Flight Center in Alabama and Kennedy Space Center in Florida. The Thiokol engineers presented their data. They recommended against launching at temperatures below 53 degrees. They showed the correlation between cold temperatures and O-ring damage. Their recommendation was clear: do not launch. And here's where the human story gets painful. NASA managers pushed back. Lawrence Malloy, the solid rocket booster project manager at Marshall, reportedly said something to the effect of, "My God, Thiokol, when do you want me to launch? Next April." The pressure was intense. The launch had already been delayed several times. There was media attention, partly because Krista McAuliffe, a school teacher from New Hampshire, was on board as part of the Teacher in Space program. Millions of school children were going to watch the launch live. Thiokol's managers asked for a 5-minute offline caucus. During that caucus, something shifted. The senior vice president, Jerry Mason, turned to Bob Lund, the vice president of engineering, and said, "Take off your engineering hat and put on your management hat." Think about what that sentence means. It means stop thinking about what the data tells you and start thinking about the schedule, the customer, the business relationship. Lund changed his recommendation. Thiokol gave NASA a new recommendation: proceed with the launch. Boisjoli and his fellow engineer Arnie Thompson tried to argue further, but they were overruled. Boisjoli later testified that he went home that night and told his wife he was afraid the shuttle would blow up. He couldn't sleep. He didn't know exactly what would happen, but he knew the O-rings would be operating far outside any conditions they'd ever been tested in, and the data told him that was dangerous. The morning of January 28, 1986, was bitterly cold. Ice had formed on the launch pad structure overnight. The temperature at launch time was 36 degrees Fahrenheit, 15 degrees colder than any previous shuttle launch. The O-rings in the right solid rocket booster's aft field joint were somewhere around 28 degrees, because that joint happened to be on the shaded windward side of the stack. At 11:38 a.m. Eastern Time, Challenger lifted off. High-speed cameras later revealed something that the naked eye couldn't see. Within the first second of ignition, a puff of dark smoke appeared at the aft field joint of the right solid rocket booster. The primary O-ring had failed to seal. Hot combustion gases at roughly 5,000 degrees Fahrenheit were pushing past it. The secondary O-ring, also cold stiffened, also failed to seal properly. For a few seconds, aluminum oxides from the burned fuel temporarily plugged the gap, a kind of accidental fragile seal. The shuttle climbed. Everything looked normal on telemetry. But 58 seconds into the flight, wind shear, high-altitude winds, began buffeting the vehicle, flexing the joints, and that temporary plug broke free. A plume of flame began jetting from the side of the right booster, aimed directly at the external tank. The flame burned through the lower strut, attaching the booster to the tank, and then breached the tank itself, which held liquid hydrogen and liquid oxygen. At 73 seconds after launch, the external tank ruptured. The vehicle broke apart in a massive aerodynamic event, not technically an explosion in the traditional sense, but a rapid structural disintegration as the fuel ignited and the aerodynamic forces tore the orbiter apart. The crew cabin, which was reinforced, likely survived the initial breakup relatively intact. Evidence later suggested that at least some of the crew were conscious for a period after the breakup. Several personal egress air packs had been manually activated, something that would only happen if someone was aware enough to reach for them. The cabin fell for 2 minutes and 45 seconds before hitting the Atlantic Ocean at roughly 200 miles per hour. The impact was not survivable. 7 people died that morning. Dick Scobie, Michael Smith, Judith Resnick, Ellison Onizuka, Ronald McNair, Gregory Jarvis, Krista McAuliffe. The nation watched it happen live on television. School children watched it happen live in their classrooms. The investigation that followed, the Rogers Commission, chaired by former Secretary of State William Rogers, became one of the most important engineering investigations in history, in part because of one commission member in particular. Richard Feynman, the Nobel Prize-winning physicist, brought a relentless, almost childlike insistence on understanding the actual engineering. In one of the most famous moments in the history of public testimony, Feynman took a small piece of O-ring material, clamped it in a C-clamp, and dropped it into a glass of ice water during a televised hearing. When he removed the clamp, the rubber didn't spring back. It just sat there, compressed, sluggish. He held it up and said simply that he believed this had some significance for the problem. It was a devastating demonstration. The entire disaster, distilled into a glass of ice water and a piece of rubber. But Feynman went further. In his appendix to the commission report, which NASA initially tried to suppress, he wrote something that cuts to the heart of not just the Challenger disaster, but every organizational failure in engineering history. He wrote that NASA management had been estimating the probability of shuttle failure at roughly 1 in 100,000. The engineers, the people actually working with the hardware, estimated it at closer to 1 in 100. That's a 1,000-fold difference. Feynman wrote, "For a successful technology, reality must take precedence over public relations, for nature cannot be fooled." The shuttle program was grounded for nearly 3 years after Challenger. The solid rocket boosters were redesigned with a third O-ring and a heater system for the joints. New safety procedures were implemented. An Office of Safety, Reliability, and Quality Assurance was established, reporting directly to the NASA administrator. The culture was supposed to change, and in many ways it did, for a while. But here's the uncomfortable truth about organizational memory, and it connects to something we've already seen with the Soviet program after Komarov, after Soyuz 11. Institutions learn from disasters, but they also forget. The people who lived through the trauma eventually retire. New people come in who know the rules but don't feel the weight of why those rules exist. The urgency fades, budget pressures return, schedule pressures return, and slowly, almost imperceptibly, the boundaries start to shift again, which is exactly what happened in the years leading up to the Columbia disaster. And to understand Columbia, you have to understand foam. Which sounds absurd, right? Foam. The stuff you think of as packing material, insulation on a coffee cup, something soft and harmless. But in the world of the space shuttle, foam became a killer, and the story of how that happened is one of the most instructive, and frankly, one of the most heartbreaking examples of normalization of deviance you'll ever find. Let's set the scene. The space shuttle's external tank, that big orange cylinder that dominates every launch photo, was essentially a giant thermos. It held about 500,000 gallons of liquid hydrogen and liquid oxygen, supercooled to cryogenic temperatures. Liquid hydrogen sits at around -423 degrees Fahrenheit. That's cold enough that if you left the tank bare, ice would form all over it from the humid Florida air, and chunks of that ice could break off during launch and damage the orbiter. So the tank was coated in a layer of spray-on foam insulation, technically called SOFI, spray-on foam insulation. It was a polyurethane-based material applied by hand in many areas, and it served a simple purpose: keep the cold in, keep the ice from forming. Now here's the thing about this foam. It was light. A chunk the size of a suitcase might weigh only about 1.5 pounds. And because it was so light, and because it was, well, foam, there was a deeply ingrained assumption within NASA that foam couldn't really hurt anything. It was soft. It was fragile. You could crumble it in your hands. How could something like that damage the reinforced carbon-carbon panels on the leading edge of the shuttle's wing? Panels designed to withstand the searing heat of re-entry? The answer, of course, is velocity. And this is where the physics matters, so let's think about it for a second. During launch, the shuttle is accelerating rapidly. If a piece of foam separates from the external tank, the foam immediately begins to decelerate. It's light. It catches the airstream. It slows down fast. But the shuttle itself keeps accelerating. So from the shuttle's perspective, that chunk of foam is now coming at the wing at a tremendous relative velocity. We're talking somewhere around 500 to 600 miles per hour. And at that speed, even 1.5 pounds of foam carries an enormous amount of kinetic energy. Think about it like this. If someone tossed a foam cooler at you underhand, you'd barely flinch. But if that same cooler hit you at the speed of a bullet, it would go right through you. Same object, radically different outcome, because kinetic energy scales with the square of velocity. Double the speed, quadruple the energy. Foam had been shedding from the external tank since the very first shuttle mission, STS-1, back in April 1981. This is a critical detail. It wasn't a new problem. It wasn't a surprise. Over the life of the shuttle program, engineers documented foam loss on mission after mission after mission. Sometimes small pieces, sometimes disturbingly large ones. And each time, When the orbiter came back intact, the conclusion was essentially, well, it didn't cause a catastrophe this time, so it must be acceptable. Sound familiar? It should. It's exactly the same logic that crept into the O-ring assessments before Challenger. Each successful flight with a known anomaly became evidence that the anomaly was tolerable, rather than evidence that they were getting closer to the edge of a cliff. There's actually a term for this in risk analysis. It's called the success bias, or sometimes outcome bias. You judge the safety of a system by the fact that nothing bad has happened yet, rather than by analyzing whether the conditions for something bad are present. And it's incredibly seductive because it feels rational. You have data, dozens of flights, hundreds of foam events, no loss of vehicle. The data says it's fine, except the data doesn't say that at all. The data says you've been lucky, and luck is not an engineering margin. So let's get to January 16th, 2003. Space Shuttle Columbia launches on mission STS-107. It's a science mission, 16 days of microgravity research. The crew is 7, Commander Rick Husband, pilot William McCool, mission specialists Michael Anderson, David Brown, Kalpana Chawla, Laurel Clark, and payload specialist Ilan Ramon, who was the first Israeli astronaut. 81.7 seconds after liftoff, roughly a minute and 20 seconds into the flight, a briefcase-sized chunk of foam separates from a region of the external tank called the bipod ramp. This is a wedge-shaped foam structure that covers the forward attachment point where the orbiter connects to the tank. The foam strikes the leading edge of Columbia's left wing, right around a reinforced carbon-carbon panel known as Panel 8. Now, nobody on the ground saw this happen in real time with any clarity, but the next day, engineers reviewing the launch footage spotted it, and this is where the story becomes about people, about organizational structure, about who gets heard and who gets silenced, because engineers saw the foam strike and they were worried. Specifically, a group of engineers at NASA and at Boeing was the prime contractor for the orbiter, began trying to assess the damage. They wanted imagery. They wanted someone to photograph the wing, either using ground-based telescopes or Department of Defense assets, or even by having the crew perform a spacewalk or use the shuttle's robotic arm to inspect the area. They made requests. They pushed. And they were turned down. Here's what's really painful about this. The requests went up the chain of management and were essentially deflected. Linda Ham, who chaired the mission management team, became a central figure in the post-disaster investigation. The prevailing management position was that foam strikes were a known and accepted phenomenon, that there was nothing that could be done about it, even if damage were found, and that requesting imagery from the Department of Defense would be an unnecessary escalation. There's a phrase that came up in the investigation that still haunts people who study organizational failures. The management team treated the foam strike as a turnaround issue, meaning something to look at after the shuttle landed and was being prepared for its next flight, rather than as an in-flight safety of flight issue. They categorized it wrong. They put it in the wrong mental box, and that categorization error was fatal. Think about what that means. Engineers were raising their hands, saying, "We think the wing might be damaged. We need to look." And the management response was essentially, "Foam has hit the shuttle before, and it's always been fine," which was true in a narrow sense. No shuttle had been lost to foam damage before. But it ignored the physics. It ignored the size of this particular foam strike, which was significantly larger than most previous events. And it ignored the specific vulnerability of the reinforced carbon-carbon panels, which were strong against heat but brittle against impact. They weren't metal. They were a carbon composite, and they could crack or shatter in ways that weren't always visible from the outside. There were engineers who lost sleep over this during the mission. Rodney Rocha, NASA's chief structural engineer for the thermal protection system, sent emails, made phone calls, tried to get the imagery request elevated. He later testified that he felt he had been silenced, not threatened, not explicitly told to shut up, just not heard. His concerns were acknowledged and then set aside. The system absorbed his warnings without acting on them. And this is a pattern we've seen before, isn't it? Roger Boisjoli before Challenger, the engineers who flagged the 200 known defects on Soyuz 1. The technical people see the danger, but the organizational structure, the hierarchy, the schedule pressure, the cultural assumptions, filters out the signal before it reaches the people with the authority to act. Columbia spent 16 days in orbit. The crew conducted their experiments. By all accounts, it was a successful mission. They had no idea, and this is something that's hard to sit with, they had no idea that a hole roughly 6 to 10 inches across had been punched in the leading edge of their left wing. On February 1st, 2003, Columbia began its re-entry into Earth's atmosphere. And this is where the physics becomes merciless. During re-entry, the shuttle encounters temperatures exceeding 3,000 degrees Fahrenheit on its leading edges. The reinforced carbon-carbon panels exist specifically to handle that heat. But Panel 8 on the left wing had a hole in it, and through that hole, superheated plasma, ionized gas at thousands of degrees, began pouring into the internal structure of the wing. It melted the aluminum structural spars. It burned through wiring. It destroyed the hydraulic lines. The wing began to lose structural integrity from the inside out. The first signs appeared in the telemetry around 8:49 a.m. Eastern Time, about 7 minutes before the shuttle was due to land at Kennedy Space Center. Temperature sensors on the left wing began reading off scale. Then they stopped reading entirely. Tire pressure sensors on the left landing gear showed anomalous readings. The tires were in the wheel well inside the wing, and they were being destroyed by the heat breach. The crew received a call from Mission Control mentioning the tire pressure readings, and Commander Husband began to respond. "Roger, and the transmission cut off. Columbia broke apart over Texas and Louisiana at an altitude of roughly 200,000 feet, traveling at more than 12,000 miles per hour. All 7 crew members were killed. The debris field stretched across East Texas and into Louisiana, covering an area roughly 250 miles long and 10 miles wide. More than 84,000 pieces of the shuttle were eventually recovered by search teams, volunteers, law enforcement, NASA personnel, walking through forests, fields, and swamps. It was the largest ground search in American history at that point. The Columbia Accident Investigation Board, chaired by retired Admiral Harold Gaiman, spent 7 months investigating. And their report, published in August 2003, is one of the most important documents in the history of engineering safety. Not just because of what it found about the foam strike, though the physical cause was clear, and they confirmed it with a dramatic test in which they fired a foam block from an air cannon at a reinforced carbon-carbon panel and blew a hole right through it, proving once and for all that foam at those velocities was absolutely capable of catastrophic damage. But the report went much further than the physical cause. It indicted NASA's organizational culture in terms that deliberately echoed the Rogers Commission findings after Challenger, 17 years earlier. The board wrote that the organizational causes of the Columbia accident were so similar to those of Challenger that it is fair to say that the Challenger Accident Investigation Board's recommendations were not followed. Think about the weight of that sentence. 17 years, billions of dollars in safety improvements, New offices, new procedures, new oversight structures, and the fundamental cultural problem, the tendency to normalize risk, to let schedule and budget pressures override engineering judgment, to silence dissenting voices through organizational inertia rather than through explicit suppression. That problem had regenerated. The reforms had addressed the symptoms. They hadn't cured the disease. And this is the thing that makes Columbia arguably even more disturbing than Challenger, at least from a systems engineering perspective. Challenger, you could argue, was a wake-up call. The organization didn't know how badly its culture had degraded. But after Challenger, they knew. They studied it. They named it. Diane Vaughan literally wrote a book about it, The Challenger Launch Decision, coining the term normalization of deviance and laying out exactly how it works. And then NASA did it again, with a different technical system in a different decade, with different people in the key roles. The same organizational pathology produced the same outcome, which tells you something profound about the nature of these failures. They're not about individual bad actors. Linda Ham wasn't a villain. She was a competent manager operating within a system that had gradually, invisibly shifted its risk tolerance over years of successful flights. The system was the problem, and systems are harder to fix than hardware. The Columbia board made 29 recommendations, and one of the most significant was that NASA should develop a means of inspecting the shuttle's thermal protection system in orbit and have a credible repair capability or rescue plan for every mission. This led to the development of the Orbiter Boom Sensor System, a 50-foot extension to the shuttle's robotic arm fitted with cameras and laser scanners, and to a policy that for most subsequent missions, the shuttle would fly to the International Space Station, where the crew could shelter if their vehicle was found to be damaged. For the few missions that couldn't reach the station, like the Hubble servicing missions, a second shuttle would be prepared on the launch pad for a potential rescue flight. But perhaps the most consequential outcome of Columbia was the decision, announced by President George W. Bush in January 2004, to retire the space shuttle entirely once construction of the International Space Station was complete. The shuttle had been sold as a routine, airline-like space transportation system. It was never that. It was an experimental vehicle, extraordinarily complex, with failure modes that could not be fully eliminated. After 14 more years of service and 22 more missions, the shuttle flew for the last time on July 21, 2011, when Atlantis landed at Kennedy Space Center. And with that landing, the United States lost its ability to launch humans into space from its own soil, a capability it wouldn't regain until 2020, when a very different kind of vehicle, built by a very different kind of organization, carried astronauts to the station. But that's a story we'll get to. For now, what I want you to hold on to is this thread that runs through everything we've talked about so far. From Nedelin's impatience on the launch pad, to the political pressure that sent Komarov up in a spacecraft with 200 known defects, to the valve that killed the Soyuz 11 crew, to the O-rings that engineers warned about and managers dismissed, to the foam that everyone knew was shedding but no one treated as dangerous until it was too late. In every case, the physics was knowable. The engineering was understood, or could have been understood, if the right questions had been asked and the right people had been heard. What failed was the human system around the engineering, the decision-making, the communication, the culture. And what makes this so hard to solve is that these human failures don't look like failures while they're happening. They look like pragmatism. They look like experience. They look like confidence. The boundaries erode so gradually that no single decision feels like the one that crosses the line. Which brings us to a different kind of space disaster, one that doesn't involve a launch or a re-entry, but something that might seem much simpler and much safer: getting a spacecraft to another planet. And the story I'm thinking of involves 2 missions to Mars, launched within weeks of each other in late 1998, both of which were lost for reasons that are almost embarrassingly simple. And I say embarrassingly not to be cruel, but because the people involved, brilliant, dedicated engineers and scientists, would be the first to use that word. Because these weren't mysteries. These weren't unknowable physics problems or exotic material failures. These were the kinds of mistakes that make you put your head in your hands and stare at the floor. Let's start with the first one: Mars Climate Orbiter. It launched on December 11th, 1998, aboard a Delta II rocket from Cape Canaveral, and for the next 9.5 months, everything looked fine. The spacecraft was on its way to Mars, where it was supposed to slip into orbit and study the planet's atmosphere and climate, temperature profiles, dust levels, water vapor, that kind of thing. It was a relatively small, relatively inexpensive mission, part of NASA's faster, better, cheaper philosophy that had taken hold in the 1990s under Administrator Dan Goldin. And we should talk about that philosophy, because it matters enormously to what happened. After the enormous cost overruns and glacial pace of earlier missions, Goldin pushed NASA's Jet Propulsion Laboratory and its contractors to build spacecraft faster, for less money, with smaller teams. And to be fair, it worked sometimes. Mars Pathfinder in 1997, the one with the little Sojourner rover, was a genuine triumph of that approach. Landed on Mars for about $150 million, sent back incredible images, captured the public's imagination. So the model seemed validated. But here's the thing about faster, better, cheaper, and this is something engineers will tell you with a kind of weary resignation. You can usually pick 2 out of 3. You can have it fast and cheap, but it probably won't be better. You can have it better and cheaper, but it won't be fast. The phrase itself was aspirational, almost a slogan, and slogans have a way of becoming pressure to cut corners, to reduce testing, to shrink teams beyond what's safe, to skip the reviews that feel redundant until the one time they're not. So Mars Climate Orbiter is cruising toward Mars, and on September 23, 1999, it executes its orbital insertion burn. It's supposed to pass behind Mars, fire its main engine to slow down, and settle into orbit about 150 to 170 kilometers above the surface. That's the target altitude. Low enough to do useful science, high enough to be safely above the atmosphere. And the spacecraft goes behind Mars, right on schedule, and the signal drops out, which is expected because Mars is blocking the line of sight to Earth. The team at JPL waits and waits, and the signal never comes back. What happened? The spacecraft came in too low, way too low. Instead of 150 kilometers, it passed through the atmosphere at roughly 57 kilometers above the surface. At that altitude, the atmosphere is thin, but it's not nothing. And the spacecraft either broke apart from aerodynamic stress or skipped off the upper atmosphere and tumbled away into a trajectory from which it never recovered. Either way, it was gone. $125 million gone. And the reason that still makes engineers wince when you bring it up, was a unit conversion error. One piece of software, provided by the spacecraft's builder, Lockheed Martin, was outputting thruster force data in pound-force seconds. English units, imperial units, and another piece of software at JPL which was using that data to calculate trajectory corrections, was expecting the numbers in Newton seconds. Metric units. 1 pound force is about 4.45 newtons, so every single trajectory correction maneuver over the entire 9-month cruise was off by a factor of roughly 4.5. The errors were small individually, tiny thruster firings to keep the spacecraft on course, but they accumulated, nudging the trajectory just slightly wrong again and again and again, until by the time it reached Mars, the navigation was off by nearly 100 kilometers. Now, you might be thinking, how is that possible? How does a mistake that basic get through? And that's the right question, because the error itself isn't really the story. Mistakes happen. Humans make errors. That's why you have checks and reviews and verification processes. The real story is that the checks failed too. There were actually people on the navigation team who noticed anomalies during the cruise. The trajectory correction seemed larger than expected. The numbers didn't quite add up, but the concerns were either not escalated forcefully enough or were explained away. Sound familiar? It should. It's the same pattern. Information existed within the system that could have identified the problem, but the organizational channels for acting on that information were inadequate. And here's what makes it sting even more. There's a standard in aerospace, and had been for years, that NASA missions should use metric units. It was established after earlier confusion precisely to prevent this kind of thing. But in the faster, better, cheaper environment, with reduced oversight and smaller teams, the interface between Lockheed Martin's software and JPL's software wasn't verified with the rigor it needed. The assumption was that everyone was speaking the same language. And you know what they say about assumptions. Now let's talk about the second mission, because it launched just a few weeks later, and its fate is, if anything, even more frustrating. Mars Polar Lander. It lifted off on January 3, 1999, headed for the south polar region of Mars, where it was supposed to land and study the soil and climate near the Martian South Pole. It also carried 2 small penetrator probes called Deep Space 2 that were supposed to slam into the surface at high speed and burrow in to test for subsurface water ice. The whole package arrived at Mars on December 3, 1999, just a couple months after the Climate Orbiter was lost, and NASA was already reeling from that failure, already conducting reviews, already asking hard questions. The pressure on this mission to succeed was immense. Mars Polar Lander entered the Martian atmosphere, and the last signal was received just before atmospheric entry. After that, silence. The lander never called home. Neither did the Deep Space 2 probes. Everything was lost. The investigation that followed couldn't determine the cause with absolute certainty because there was no telemetry, no data stream from the spacecraft during the critical descent phase because the mission design didn't include real-time data transmission during landing. Think about that for a second. The spacecraft was attempting the most dangerous part of its entire mission, descending through an alien atmosphere and landing on another planet. And it was doing it in silence, with no way for anyone on Earth to know what was happening until it was over. That was a cost-saving decision. Transmitting data during descent would have required more complexity, more hardware, more testing, more money. Faster, better, cheaper. But the Failure Review Board, led by John Cassani at JPL, identified the most probable cause, and it's one of those things that makes you want to scream. The lander used 3 legs that deployed during descent. Each leg had a sensor, a simple contact sensor like a switch, that was supposed to detect the moment the leg touched the Martian surface. When the software received the signal that the legs had touched down, it would shut off the descent engines. That's the sequence. Legs touch ground, sensors trigger, engines cut off, you're landed. Simple, right? Here's what likely happened. During descent, when the legs deployed, swinging down and locking into position, the mechanical jolt of deployment generated a spurious signal. A false positive. The contact sensors registered a bump and briefly indicated contact, even though the spacecraft was still about 40 meters above the surface. And the software, doing exactly what it was programmed to do, saw that signal and shut off the engines, 40 meters up. The lander fell the rest of the way unpowered and hit the surface at roughly 50 miles per hour. At that speed, on a rocky Martian plain, there's nothing left to communicate with. And here's the kicker. This failure mode was actually known. During testing, engineers had observed that the leg deployment could generate spurious sensor readings. The issue had been identified. But the software fix, simply telling the computer to ignore contact sensor readings until the spacecraft was below a certain altitude, or until a certain time had elapsed after leg deployment, was never implemented. The problem was documented, noted, and then fell through the cracks. In a larger team, with more rigorous review processes, with the kind of redundant checking that characterized the old way of doing things before faster, better, cheaper, someone almost certainly would have caught it. Someone would have said, "Wait, did we close out that anomaly with the leg sensors?" But in the lean, stripped-down environment of late 1990s Mars missions, it slipped through. 2 missions, 2 losses. One because of a unit conversion error that should have been caught by basic interface verification. One because of a known software vulnerability that was never fixed. Combined cost, somewhere around $360 million. No lives lost, thankfully. These were robotic missions. But the scientific loss was real, and the institutional damage was severe. Dan Goldin's faster, better, cheaper philosophy didn't survive these failures intact. NASA commissioned a series of reviews, and the conclusion was stark. You can push cost and schedule only so far before you start cutting into the margin that keeps missions alive. The Mars program was restructured. Future missions got bigger budgets, more testing, more oversight. Mars Odyssey in 2001, the Spirit and Opportunity rovers in 2004, Curiosity in 2012. Each of these was built with more time, more money, and more rigor than the missions that were lost. But what I find most interesting about these 2 failures is how they fit into the larger pattern we've been tracing. Because on the surface, they look completely different from Challenger or Columbia. No crew, no dramatic explosion, no national mourning. Just a spacecraft that went quiet and never called home. But underneath, the same forces are at work. Pressure, political, budgetary, institutional, pushing the system to operate with less margin than it needs. Information that exists within the organization, but doesn't reach the people who can act on it. Known risks that get documented, but not resolved. And a culture that, in its enthusiasm for a compelling vision, in this case, the vision of exploring Mars affordably and frequently, gradually accepts levels of risk that would have been unacceptable in a more cautious era. And this is worth sitting with for a moment, because it tells us something important about the nature of these failures. They're not random. They're not bad luck. They emerge from the structure of the organizations that produce them, from the incentives and pressures and communication patterns that shape how thousands of people make thousands of small decisions every day. Change the incentives, and you change the failures. But the incentives are always being shaped by forces outside engineering, by politics, by budgets, by public expectations, by the career ambitions of leaders who need visible successes, Which brings us to a disaster that happened far from Earth, in a place where rescue was never an option, and where the margin between life and death was measured in minutes and in the pressure of oxygen inside a single module. And the story starts with a space station that, by 1997, had been in orbit for over 11 years, far longer than anyone originally planned. A station called Mir, and a series of events aboard it that would push the crew to the very edge of what human beings can endure in space. Mir launched on February 20th, 1986, just 25 days after the Challenger disaster, which is one of those coincidences that feels almost too neat. While NASA was reeling from its worst tragedy, the Soviet Union was putting the core module of what would become the most ambitious space station ever built into low Earth orbit. And the original plan was for Mir to operate for about 5 years. 5 years of continuous habitation, a rotating cast of cosmonauts conducting experiments, testing long-duration spaceflight, pushing the boundaries of how long humans could live and work off the planet. 5 years. That was the design life. By 1997, Mir had been up there for 11 years, more than double its intended lifespan. And here's the thing about machines in space. They don't age gracefully. On Earth, you can patch a leaky roof, replace a corroded pipe, call a technician when the air conditioning starts making that weird noise. In orbit, 250 miles above the ground, traveling at 17,000 miles per hour, your options are a lot more limited. You can fix what you have the parts for. You can jury-rig solutions with whatever's on hand, but you can't call a plumber. And over 11 years, things accumulate. Small problems that aren't quite worth the effort to fix. Workarounds that become permanent. Systems running on backup modes that were never meant to be the primary modes. Mir, by the mid-90s, was showing its age in ways that ranged from annoying to genuinely alarming. Mold was growing on the walls and behind panels, actual fungal colonies thriving in the humid, warm environment of a space station. Some of this mold was eating into the rubber seals around windows. Coolant loops had developed leaks, and droplets of ethylene glycol, antifreeze basically, would occasionally float through the cabin. The station's orientation control system was temperamental. Electrical systems had degraded. But Mir was still flying. It was still inhabited. And it had become a source of enormous national pride for Russia, which by this point was no longer the Soviet Union, but a country going through the most wrenching economic and political transformation of the 20th century. The Russian space program was starved for funding. Salaries went unpaid. Facilities deteriorated. And yet, Mir kept going, because it was one of the few things Russia could still point to and say, "We are still a great spacefaring nation." The political pressure to keep Mir operational was immense, even as the station's systems grew increasingly unreliable. And there was another dimension to this. In the early 90s, NASA and the Russian space agency Roscosmos had entered into a partnership, the Shuttle Mir program, where American astronauts would live aboard Mir for extended stays, and the space shuttle would dock with the Russian station. This was partly about science, partly about diplomacy, and very much about keeping Russian aerospace engineers employed and engaged so they wouldn't sell their expertise to countries you'd rather not have it. The United States was literally paying Russia to participate, and American astronauts were living aboard this aging station, which meant that when things went wrong on Mir in 1997, it wasn't just a Russian problem. It was an international incident. So let's talk about what went wrong, because 1997 aboard Mir was one of the most harrowing years in the history of human spaceflight, and it happened not in a single dramatic moment, but as a cascade of emergencies that just kept coming. The crew at the center of the worst of it included Commander Vasily Tsibliev, flight engineer Alexander Lazutkin, and American astronaut Jerry Linenger, who would later be replaced by Michael Foale. And the trouble started on February 23, 1997, with a fire. Now, fire in space is one of those things that sounds scary in the abstract, but the reality is even worse than you'd imagine. On Earth, fire is dangerous, obviously, but on Earth, you can run. You can open a window. You can get outside. In a space station, there is no outside. The entire volume of breathable air is contained in those modules. And if that air fills with smoke and toxic combustion products, you have nowhere to go. Your escape route is a Soyuz capsule that takes time to prepare for departure. And if the fire is between you and the Soyuz, you might not be able to reach it at all. The fire started in an oxygen-generating canister, a solid-fuel oxygen generator, sometimes called a candle, which is a device that produces breathable oxygen through a chemical reaction. You light it, essentially, and it burns slowly, releasing oxygen. These were supplemental systems, used in addition to the main electrolysis units that split water into hydrogen and oxygen. On this particular evening, Lazutkin activated one of these canisters, and instead of the normal, controlled reaction, the thing essentially turned into a blowtorch. Flames shot out, reportedly reaching lengths of 2 to 3 feet, and the module began filling with thick, acrid smoke. Think about that for a second. You're in a metal tube the size of a school bus, floating in microgravity, and a jet of flame is burning in front of you, while smoke fills the air you need to breathe. The crew grabbed fire extinguishers and oxygen masks, but the masks were the kind that generated their own oxygen, and some of them didn't work properly. Linenger, the American astronaut, later described the smoke as so thick he couldn't see his hand in front of his face. The fire burned for about 14 minutes before it finally exhausted itself. 14 minutes. That doesn't sound long, but when you're sealed inside a spacecraft with a fire you can't fully control, every second stretches. The crew survived. No one was seriously injured, though they spent the next several days dealing with residual smoke and monitoring the air quality. But the fire exposed something deeply troubling. The station's safety systems, its emergency procedures, its equipment, all of it was showing the strain of operating far beyond design life with insufficient maintenance and resupply. And here's where the pattern we've been following shows up again. Those solid fuel oxygen generators had a known history of problems. There had been previous incidents, not as severe, but enough to raise concerns. The canisters were old. The procedures for using them hadn't been updated to reflect the station's degraded condition. The risk was known, documented, and accepted. And then, before anyone had fully recovered from the fire, things got worse. On June 25th, 1997, 4 months later, with a different American astronaut aboard, Michael Foale having replaced Linenger, the crew was conducting a manual docking test with an unmanned Progress cargo vessel. Now, Progress ships are the workhorses of space station resupply. They're uncrewed capsules that bring food, water, equipment, and fuel up to the station, and they normally dock automatically using a system called KURS. But the KURS system was expensive, and the Russian Space Agency was exploring whether they could save money by using a manual docking approach called Toru, where a cosmonaut on the station would guide the Progress in using a joystick and a video feed from a camera on the approaching vessel. They had tried this before, in March, and it hadn't gone well. The Progress had come in too fast, and Tsibliev had to abort. Ground controllers decided to try again, and this is one of those decisions that, in hindsight, is almost incomprehensible. The first attempt had nearly ended in collision. The crew was exhausted, the station was in rough shape, and yet the pressure to demonstrate that manual docking could work, because it would save money, because it would prove a capability, pushed them to try again. On June 25th, Tsibliev was at the Toru controls, watching the video monitor as the progress approached. But the video feed was poor. The image was washed out by sunlight, and it was difficult to judge distance and closing speed. The progress was coming in too fast. Tsibliev tried to break it, tried to steer it away, but the commands weren't responding the way he expected. Foal, looking out a window, saw the progress heading directly toward the Spectre module and shouted a warning. The progress struck Spectre. It punctured the module's hull. And now you have the thing every astronaut and cosmonaut fears most, the thing that makes your blood go cold just thinking about it. A depressurization event. Air, their air, the only air they had, began rushing out through the breach. The pressure alarms went off. The crew could hear the hiss. Foal later said he could feel the pressure change in his ears, like descending in an airplane, but faster. They had minutes, maybe less. The Spectre module had to be sealed off from the rest of the station, which meant closing the hatch between Spectre and the node it was connected to. But here's the problem. Cables ran through that hatchway. Power cables, data cables, all sorts of umbilicals connecting Spectre's solar arrays to the rest of the station's electrical grid. You couldn't just slam the hatch shut. Someone had to disconnect those cables first, and they had to do it while the air was bleeding out of the station, and every second counted. Lazutkin dove toward the hatch. He began pulling cables, disconnecting them as fast as he could. Some he couldn't disconnect. He cut them. And finally, working with desperate speed, they got the hatch closed and sealed. The pressure stabilized. They were alive, but they'd lost Spectre. The module was sealed off, depressurized, gone. And with it, they'd lost a significant portion of the station's electrical power because Spectre's solar arrays had been major contributors to Mir's power grid. The station went into a slow tumble because the attitude control system was disrupted. They lost orientation toward the sun, which meant the remaining solar arrays couldn't charge properly. Power dropped. Systems began shutting down. Communications with the ground became intermittent. For several hours, the crew of Mir was essentially in a crippled, tumbling spacecraft with failing power and limited communication, trying to stabilize the situation using procedures they were improvising in real time. Foal, drawing on his background in astrophysics, helped figure out the station's rotation rate by observing the movement of stars through a window, which allowed them to calculate the right thruster firings to stop the tumble and reorient toward the sun. They saved the station, but just barely, and the aftermath was brutal. Tsibliev, who had been at the controls during the collision, was widely blamed, though the investigation made clear that the real problems were systemic. The pressure to conduct the manual docking test, the inadequate video system, the exhaustion of the crew, the decision to retry after a failed first attempt. Tsibliev developed a heart irregularity during the mission, likely from stress. He never flew in space again. The Mir crises of 1997 prompted a fierce debate within NASA about whether it was safe to continue sending American astronauts to the station. Frank Culbertson, who managed the Shuttle Mir program, argued for continuing. Others, including the NASA Inspector General, raised serious concerns. Congress got involved. In the end, the program continued. The diplomatic and political stakes were simply too high to walk away. But the experience profoundly shaped how NASA approached the International Space Station, which was then being designed and would begin construction in 1998. And this is where the Mir story connects to something larger, something that brings us forward into the 21st century and into a different kind of space disaster. One that doesn't involve fire or depressurization or collision, but rather the quiet, invisible accumulation of risk in a program that everyone believed was safe, precisely because it had been operating successfully for so long. Because if Mir taught anything, it was that success can be the most dangerous thing in the world. Every day the station didn't fail reinforced the belief that it wouldn't fail. Every close call that ended well became evidence that the system was resilient rather than lucky. And that same pattern, success breeding complacency, experience breeding overconfidence, was already at work in another program, one we've already talked about, in the years between Challenger and Columbia. But it also shows up in a disaster we haven't discussed yet, one that happened not in orbit, but on the launch pad. And not to astronauts, but to the ground infrastructure that makes spaceflight possible. A disaster that reminds us that the most dangerous moment in any space mission isn't always the one that gets the headlines. Sometimes it's the moment nobody's watching at all. On August 22, 2003, just 6 months after Columbia broke apart over Texas, a Brazilian rocket called the VLS-1 was sitting on its launch pad at the Alcantara Launch Center, which is located on Brazil's northern coast, right near the equator. And this is a detail worth pausing on for a second, because Alcantara's location is actually one of the most coveted pieces of launch real estate on the planet. Being close to the equator means you get a significant boost from the Earth's rotation when you're launching eastward. It's free velocity, essentially. The European Space Agency launches from French Guiana for the same reason. So Brazil had this incredible geographic advantage, and they'd been working for decades to develop their own independent launch capability. A homegrown rocket program that would let them put satellites into orbit without having to pay the Americans or the Europeans or the Russians to do it for them. The VLS program, Veículo Lançador de Satélites, which just means satellite launch vehicle, had been in development since the 1980s. It was a modest rocket by global standards, a solid-fueled vehicle designed to put small satellites into low Earth orbit. Brazil had attempted 2 launches before, in 1997 and 1999, and both had failed. The first veered off course and had to be destroyed. The second suffered a second-stage ignition failure. So by 2003, there was enormous pressure, political pressure, institutional pressure, personal pressure, to make the third attempt work. The launch was scheduled for a few days later, and technicians were on the pad preparing the vehicle. Here's what you need to understand about solid rocket motors. Unlike liquid-fueled engines, which you can start and stop by opening and closing valves, a solid motor is essentially a giant, carefully shaped block of propellant packed inside a casing. Once it ignites, it burns until the fuel is gone. There is no off switch. This is the same basic technology as a firework, just scaled up enormously and engineered with extraordinary precision. The VLS-1 had 4 solid rocket boosters strapped around its first stage, and on that August afternoon, technicians were performing final checks on the vehicle when one of those boosters ignited spontaneously. Just think about that for a second. You're standing next to a rocket on a launch pad, running through your checklist, and one of the motors just lights. No countdown, no warning, no command signal, just sudden, catastrophic ignition. The fire triggered the other boosters almost immediately. The entire vehicle was engulfed. 21 people were killed: technicians, engineers, scientists. 21 people who were not astronauts, who were not flying into space, who were doing the unglamorous, essential groundwork that makes any launch possible. It was the deadliest disaster in Brazilian space program history, and one of the worst launch pad accidents anywhere since the Nedelin catastrophe back in 1960. The investigation that followed pointed to an electrical fault, a stray signal that reached the igniter of one of the solid boosters. The exact pathway of that signal was debated, but the broader picture was painfully familiar. The program had been underfunded for years. Safety protocols had eroded. There was schedule pressure to get the launch done. Equipment was aging, and the organizational culture had developed that same dangerous tolerance for risk that we've seen over and over again, at NASA with Challenger, at NASA again with Columbia, aboard Mir. The details change, the continent changes, the language changes, but the pattern is the same. Brazil's space program was devastated, not just by the loss of life, which was staggering, but by the loss of expertise. In a small national program, 21 people represent an enormous fraction of your institutional knowledge. It's not like losing 21 people at NASA, which employs tens of thousands. For Brazil, it was like losing an entire generation of rocket engineers in a single afternoon. The program essentially stalled for years. They've been working to recover ever since, and Alcântara is still an active launch site today. In fact, there's been a technology safeguards agreement with the United States signed in 2019 that opens the base to commercial launches. But the VLS program itself never really recovered from that day. And this disaster matters for our story because it illustrates something that the more famous accidents sometimes obscure. We tend to think of space disasters as things that happen during flight. Rockets exploding after liftoff, capsules burning on re-entry, spacecraft lost in the void between planets. But a huge amount of the risk in spaceflight lives on the ground. The people who fuel the rockets, who wire the igniters, who bolt the heat shields in place, who inspect the tiles one by one, they are exposed to genuinely dangerous systems every working day. And when safety culture degrades, they're often the first to pay the price. Now, I want to bring us forward from 2003 into the era that shaped how we think about space safety today, because something really important was happening in the years after Columbia. NASA was winding down the shuttle program. We talked about Bush's 2004 decision to retire the fleet, and the agency was trying to figure out what came next. The Constellation program was supposed to build new vehicles to go back to the moon, but it ran into budget problems and was eventually canceled under the Obama administration in 2010. And in the gap that opened up, something genuinely new started to happen. Private companies began to take on a much larger role in getting things, and eventually people, to orbit. SpaceX, founded by Elon Musk in 2002, is the most prominent example. But there was also Orbital Sciences, now Northrop Grumman, and later Boeing with their Starliner capsule, and Sierra Nevada with their Dream Chaser spaceplane. NASA's Commercial Crew and Commercial Cargo programs were designed to let these companies develop their own vehicles, while NASA provided funding and oversight. And this was a genuinely different model from how things had worked before. During the shuttle era, NASA designed the vehicle, NASA built the vehicle, or rather, NASA managed the contractors who built the vehicle. But NASA owned the design and made the decisions. Under the commercial model, the companies own the designs. NASA is a customer, not the architect. And here's where it gets interesting from a safety perspective. Because when SpaceX was developing the Falcon 9 rocket and the Dragon capsule, they had failures. Real, spectacular, public failures. In June 2015, a Falcon 9 broke apart about 2 minutes after launch, destroying a Dragon cargo capsule headed for the International Space Station. The cause was a faulty strut inside the second-stage liquid oxygen tank. A steel strut about 2 feet long that was supposed to hold down a helium pressure vessel. The strut failed at about 1/5 of the force it was supposed to handle. It was a subcontractor part, and SpaceX hadn't been testing each one individually, relying instead on certification data from the manufacturer. After the failure, they started testing every single strut. Then, in September 2016, a Falcon 9 exploded on the launch pad during a routine pre-launch fueling test at Cape Canaveral. No one was hurt. The pad was clear of personnel, but the rocket and its payload, a communications satellite, were completely destroyed. The cause turned out to be extraordinarily subtle. SpaceX uses super-chilled liquid oxygen, colder than what most other rockets use, because denser propellant means you can pack more into the same tank. But at those extreme temperatures, the helium loading system created conditions where solid oxygen could form inside the carbon composite overwrap of the helium pressure vessels. Solid oxygen in contact with carbon fiber under pressure, that's essentially a bomb waiting for a trigger. And the trigger was just the normal mechanical stresses of the fueling process. This was a failure mode that nobody had predicted. It wasn't in any textbook. It emerged from the specific combination of design choices SpaceX had made: the super-chilled oxygen, the carbon overwrap pressure vessels, the particular fueling sequence. And finding the cause took months of painstaking investigation, because the explosion happened so fast and destroyed so much of the evidence. But here's what's really worth noting. These failures happened during the development phase, before SpaceX was carrying people. And in a sense, that's exactly how you want the process to work. You fly, you fail, you investigate, you fix, you fly again. It's the old test pilot philosophy translated into the unmanned era. The Falcon 9 has since become one of the most flown rockets in history, with well over 200 successful missions. The failure rate has dropped to a level that's genuinely remarkable for a launch vehicle. And when SpaceX finally did start carrying astronauts in May 2020 with the Crew Dragon Demo 2 mission that took Doug Hurley and Bob Behnken to the ISS, the vehicle had a track record that gave people real confidence. But confidence, as we've discussed all night, is a complicated thing in spaceflight. Because the question that hangs over the commercial era is the same question that hung over the shuttle, and over Mir, and over every program that flies long enough to start feeling routine. When do you start believing your own success? When does a string of good outcomes stop being evidence of good engineering and start becoming a reason to relax your vigilance? Boeing's Starliner program offers a sobering counterpoint to the SpaceX story. Starliner's uncrewed test flight in December 2019 suffered a mission-elapsed timer error. The spacecraft's clock was off by about 11 hours from the actual mission time, which meant it burned through its maneuvering fuel at the wrong moments and couldn't reach the ISS. An independent review found over 80 corrective actions were needed, and a second uncrewed test in May 2022 revealed more issues, including problems with the propulsion system. The crewed test flight finally launched in June 2024, carrying Butch Wilmore and Suni Williams to the station, but helium leaks and thruster anomalies during the flight raised enough concerns that NASA decided not to bring them home on Starliner. As of early 2025, Wilmore and Williams remained aboard the ISS, their planned 8-day mission extended to months, waiting instead for a SpaceX Dragon to bring them back. Now, nobody was hurt. The station is safe. The astronauts are fine. But think about what that decision represents. NASA looked at the data, looked at the thruster performance, looked at the helium leaks, and said, "We are not confident enough in this vehicle to put crew inside it for re-entry." That is an extraordinary call to make. It's the kind of call that the people at Thiokol tried to make the night before Challenger and were overruled. It's the kind of call that Rodney Rocha tried to make during Columbia's mission and couldn't get anyone to listen. And the fact that NASA made it, that they chose the cautious path, even though it was embarrassing, even though it was expensive, even though it meant admitting that a program years behind schedule still wasn't ready. That tells you something about what the agency learned from its worst days. But it also raises a question that doesn't have a clean answer, and it's a question that's going to define the next era of human spaceflight as more companies, more nations, and eventually more tourists start flying. The question is this: how do you maintain that hard-won safety culture when the economics of spaceflight are changing, when there's competitive pressure to fly faster and cheaper, when success starts to feel normal, and when the people making decisions are further and further removed from the people who actually build and fly the hardware? That's the question, and it's worth sitting with for a while, because the answer isn't obvious, and the stakes are as high as they've ever been. Think about what we've been talking about all this time. Every disaster we've walked through tonight, every one, had a moment where someone knew something was wrong, or at least suspected it, and the system around them either couldn't hear it or chose not to. The engineers at the Baikonur launch pad in 1960 knew the R-16 wasn't ready, but Nedelin waved them off. The technicians who cataloged over 200 defects on Soyuz, one couldn't stop Komarov from flying because the political calendar wouldn't bend. The Apollo 1 crew had been raising concerns about the spacecraft for months. Roger Boisjoli had the data on those O-rings and begged his managers not to launch. Rodney Rocha saw the foam strike on Columbia and tried to get imaging of the wing and was told it wasn't necessary. The Brazilian engineers at Alcantara were working with equipment they knew was underfunded and aging. In every single case, the technical knowledge existed. The warning was there. What failed was the organizational pathway between the person who knew and the person who decided. And that's the thing about safety culture. It's not a technology problem. You can't engineer it into hardware the way you engineer redundancy into an avionics system. It lives in people, in relationships, in the willingness of a junior engineer to raise a hand and say, "I'm not comfortable with this," and in the willingness of a senior manager to actually stop and listen, even when stopping is expensive. It lives in the boring stuff: meeting structures, reporting chains, how dissenting opinions get documented, whether there's a formal process for escalating concerns that bypasses the normal chain of command. It's the least glamorous part of spaceflight, and it might be the most important. Now here's where the modern era gets complicated. For most of the history we've been talking about tonight, spaceflight was a government activity. NASA flew the shuttle. Roscosmos flew Soyuz. The Chinese Space Agency flies Shenzhou. Government agencies are bureaucratic and slow and sometimes maddeningly political, but they also have something that commercial companies don't always have, which is a mandate that isn't primarily about profit. NASA's mission is exploration and science and, critically, the safety of its crews. When NASA grounds a vehicle, nobody's stock price crashes. Nobody's investors start asking uncomfortable questions on an earnings call. The cost of caution is measured in schedule delays and budget overruns, which are painful but survivable. But when you shift to a model where private companies are building and operating crewed spacecraft, which is the model we're in right now, and the model that's only going to expand, the incentive structure changes in subtle ways. SpaceX is a private company. Its revenue depends on launching satellites, flying astronauts, building Starship. Boeing is a publicly traded company with shareholders expecting returns. When these companies make safety decisions, they're making them in a context where delays cost real money, where competitors are watching, where contracts can be won or lost. And that doesn't mean they don't care about safety. They absolutely do. And the people working at these companies are deeply committed to getting it right. But the pressures are different. The texture of the decision-making environment is different. And history tells us that pressure is where cracks form. Remember what happened with the shuttle program. The normalization of deviance that sociologist Diane Vaughan identified, the slow, almost imperceptible process by which anomalies that should have been alarming became accepted as routine. That didn't happen because anyone at NASA was careless or incompetent. It happened because the shuttle kept flying successfully despite the O-ring erosion, despite the foam strikes, and each successful flight became evidence that the risk was acceptable. Success is the most dangerous thing in spaceflight. It breeds confidence, and confidence, over time, can quietly erode the vigilance that made the success possible in the first place. So now imagine that dynamic playing out across an entire industry. SpaceX has launched hundreds of Falcon 9 missions. The vehicle has an extraordinary track record. It lands its boosters, it flies crew. It's become so routine that most launches barely make the news anymore. And that's wonderful. That's the dream, right? Spaceflight becoming reliable and accessible and almost ordinary. But almost ordinary is exactly the psychological territory where normalization of deviance lives. When something works 100 times in a row, the 101st time feels safe. The 200th time feels inevitable. And somewhere in there, you stop looking as hard at the data, or you start accepting small anomalies because they've never caused a problem before, or you compress your review timelines because the schedule is tight and the vehicle has proven itself. SpaceX, to their credit, seems aware of this. Their iterative testing philosophy, build it, fly it, break it, learn, rebuild, is in some ways a structural defense against complacency. When you're constantly pushing the envelope with Starship, constantly dealing with explosions and failures and redesigns, you stay in that mindset of humility. You remember that rockets are hard. But Falcon 9 is a mature vehicle now. It's not in the experimental phase anymore. And the question is whether the organizational culture that was forged in failure, in those early Falcon 1 crashes, in the 2015 strut failure, in the 2016 pad explosion, whether that culture persists as the company grows, as the workforce turns over, as the people who lived through those failures retire or move on, and are replaced by people who've only ever known success. This is the generational problem of safety culture, and it's not unique to spaceflight. You see it in aviation, in nuclear power, in offshore drilling, in medicine. The generation that lives through a catastrophe builds the safety systems. They write the procedures. They create the review boards. They insist on the checks. And it works. The system gets safer. Fewer bad things happen. And then a new generation comes in, a generation that's only ever known the safe version. And they look at all those procedures and review boards and checks and they think, why do we do all this? It's slowing us down. It's expensive. Nothing bad has happened in years. Maybe we can streamline. Maybe we can skip this one review. Maybe we don't need quite so many people looking at this data. And they're not wrong that some procedures accumulate beyond usefulness. Bureaucracy does calcify. Not every check is equally important. The challenge is knowing which ones you can safely remove and which ones are the thin line between you and catastrophe. And you often can't tell the difference until it's too late. This is why the Columbia Accident Investigation Board's report was so insistent that NASA's problems were cultural, not just technical. You can fix a technical problem. You can redesign an O-ring. You can change the foam composition on an external tank. But cultural problems regenerate. They grow back, like weeds, because they're rooted in human nature, in our tendency to discount risk when things are going well, in our reluctance to deliver bad news to people above us, in our desire to meet deadlines and keep promises and not be the person who slows everything down. So what do? How do you fight human nature? Well, one answer, and it's an imperfect one, but it's the best we've got, is institutional memory. You build it into the structure. You don't just rely on the people who remember. You create systems that remember for them. NASA's Aerospace Safety Advisory Panel, which was strengthened after Columbia, exists partly for this purpose. It's an independent body that reviews NASA's safety practices and reports directly to Congress. It can't be easily silenced or sidelined by program managers who are under schedule pressure. The panel's annual reports are public, they're on the record, and they've consistently raised concerns about the transition to commercial crew. Not because they think commercial companies are unsafe, but because they worry about the oversight mechanisms, about whether NASA has enough visibility into the internal decision-making of its commercial partners. And that's a legitimate concern. When NASA built and operated the shuttle, everything was in-house. Every design decision, every test result, every anomaly report flowed through NASA's own engineering organization. NASA's engineers could, and did, dig into the details. They could challenge assumptions. They could demand more data. With commercial crew, the relationship is different. NASA is a customer. SpaceX and Boeing own their vehicles. NASA has insight. They have safety representatives embedded in the programs. They review data. They participate in flight readiness reviews. But the dynamic is fundamentally different from when NASA owned the hardware. There are things that are proprietary. There are decisions that happen inside the company before NASA ever sees them. And the question is whether that layer of separation creates blind spots. It's worth noting that this isn't a theoretical concern. We've already seen cases where it matters. The Starliner situation, Wilmore and Williams sitting on the station for months because NASA wasn't confident in the vehicle, that happened in part because the thruster issues and helium leaks revealed gaps in Boeing's understanding of its own spacecraft's behavior. Boeing believed the vehicle was safe to fly home. NASA wasn't so sure. And NASA had the authority to make the call, and they did. But what if they hadn't? What if the contractual relationship had been structured differently? What if the pressure to demonstrate success had been just a little bit stronger? These are the kinds of questions that keep safety engineers up at night, and they're going to get more pressing as spaceflight expands. We're not just talking about NASA and its contractors anymore. We're talking about space tourism companies like Blue Origin and Virgin Galactic flying paying customers. We're talking about SpaceX's Starship, which is designed to carry dozens of people at a time and eventually fly to Mars. We're talking about China's rapidly expanding crewed program, about India's Gaganyaan, about commercial space stations being planned by Axiom and others to replace the aging ISS. The number of organizations flying humans in space is about to increase dramatically, and each one of them is going to face the same fundamental tension between ambition and caution, between schedule and safety. between the desire to push forward and the knowledge of what happens when you push too far. And here's the thing that's both sobering and, in a strange way, comforting. Every lesson we've talked about tonight, every single one, was paid for. Paid for in the most terrible currency imaginable. Valentin Bondarenko, who died in a fire in an oxygen-rich chamber in 1961, a lesson the Soviets classified and that might have saved Grissom, White, and Chaffee 6 years later if anyone had known. Vladimir Komarov, who flew a spacecraft he knew wasn't ready because the system wouldn't let him refuse. The 3 cosmonauts of Soyuz 11, Dobrovolsky, Volkov, Patsayev, who suffocated because a valve opened during separation and there was no way to close it, no pressure suits to protect them. The 7 crew members of Challenger, including Krista McAuliffe, the teacher who was supposed to inspire a generation. The 7 crew members of Columbia, including Ilan Ramon, Israel's first astronaut, who carried with him a drawing by a child who had survived the Holocaust. The 21 technicians at Alcantara who were just doing their jobs on a Friday afternoon. These are real people. They had families. They had plans for after the mission, after the shift, after the launch. And the only way to honor them, the only way any of this means anything, is to remember not just their names, but the specific, detailed, sometimes maddeningly preventable reasons they died. To remember that the O-rings lost their resilience below 53 degrees. To remember that foam had been hitting the orbiter's thermal protection system for years, and nobody fixed it because it hadn't caused a catastrophe yet. To remember that a unit conversion error between pounds and newtons can lose a spacecraft. To remember that schedule pressure and underfunding kill just as surely as hardware failures. These details matter. They're not trivia. They're the accumulated wisdom of a species learning, the hard way, how to leave its planet. So as you lie there, maybe drifting in and out, maybe half asleep already, and that's perfectly fine. That's exactly where you should be. Just carry this one thought with you. Spaceflight is the most audacious thing human beings do. We strap ourselves to controlled explosions and hurl ourselves into a vacuum where nothing about the environment is compatible with life. And we do it because we're curious, because we want to know what's out there, because something in us refuses to stay put. And every time we do it safely, it's because somewhere, someone remembered what went wrong before. Someone looked at the data one more time. Someone raised their hand in a meeting and said, "I'm not sure about this." Someone chose caution over schedule, chose honesty over comfort, chose the harder right over the easier wrong. That's the real engineering, not just the rockets and the heat shields and the life support systems, though those are magnificent. The real engineering is building organizations where the truth can travel from the person who sees it to the person who needs to hear it, without getting lost or diluted or suppressed along the way. That's the hardest system to build, and it's the one that matters most. The stars are still up there. They're patient. They'll wait for us to get it right. And in the meantime, the best thing any of us can do, whether we're engineers or astronauts or just people lying in the dark, listening to stories about how hard it all is to remember, to pay attention, to never let success make us careless. Sleep well. The universe will still be there in the morning.